Hello, this is my Physics 2211 Lab 3 Black Hole and Orbits. The purpose of part 1 of the lab is to find the mass of a black hole knowing that the mass of a star orbiting is 2 times 10 to the power of 30 kilograms. For part 2, we must find the initial velocity of a spaceship in the moon of a planet so it doesn't crash into either of them. The physics principles I will be using include Newton's second law, which states that a net force is the rate of change of momentum over time, as well as the product of mass times acceleration. This law also gives us the velocity update formula. I will also be using the position update formula and the gravitational force, which, in case that there is only one force in a system, tells us that the mass of one object is equal to the acceleration of the other object times the distance between them squared over the gravitational constant. As a preview of the results, I have found that the mass of the black hole is 8.4 times 10 to the power of 43 kilograms, and that the initial velocity of the spaceship is the vector of 25 times 10 to the power of 3, 25 times 10 to the power of 3, 0 meters per second. This is a diagram of part 3 where the star is orbiting the black hole, which is stationary, and the only force between them is the gravitational force. Here, the system is a star while the surroundings are the black hole and everything else. These are the initial conditions of my computational model, where I had the gravitational constant, the mass of the star, the initial time, and delta t, which is 1 Earth day in second. Then I calculated the net force. I found this by calculating the initial and final momentum, which are equal to the mass times the velocity. Then I found the delta of momentum and velocity by knowing that they are their final values minus their initial values. Finally, I got the net force by dividing the change in momentum over the change in time. Then I decompose the net force by finding its perpendicular and parallel components by applying the appropriate formulas displayed in this slide. This is a screenshot of my computational model, where the cyan arrow represents the perpendicular force, the magenta arrow represents the parallel force, and the orange arrow represents the net force. Each time step, the mass of the black hole is updated, using the formula derived from the gravitational force. By simplifying it further, we get that the mass of the black hole is the magnitude of delta V times the sum of x squared plus y squared divided by delta t times the gravitational constant. The computational model gives us a great amount of masses, whose average is 8.4 times 10 to the power of 43 kilograms. This is the diagram of part 2 of the lab. Here, there is a spaceship that must be in a figure-8 orbit around a planet and a moon, without crashing into either of them. Here, the system is a spaceship while the surroundings are the planet, the moon, and everything else. Here is how I calculated the forces in the spaceship and the moon. First, I found the relative position vectors, then the gravitational force were calculated using its formula, and finally the net force is calculated by summing all the forces on the object. Afterwards, I updated the position and velocity of the moon and spaceship using the position and velocity update formula. This is a screenshot of the results of my computational model reflecting the motion of the spaceship between the moon and the planet without crashing into either of them. This was achieved with a velocity vector of 25 times 10 to the power of 3, 25 times 10 to the power of 3, 0 meters per second. Some possible sources of error include assuming that the position of black hole is constant, not considering any other forces besides gravitational force, and using very short time steps for part 2. The first additional question is how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. Well, to calculate the net force, you must know all of the objects with which the system is interacting and how it interacts with them. On the other hand, to calculate a change of momentum, you must determine the motion of a system at different moments. The second question asks what will we need to include in our computational model if we wanted to predict the motion of the entire system. If we wanted to do this, we will need to consider the velocity of the black hole and all the forces that affect the system from external planets or stars, where the heaviest ones will contribute the most to the change in momentum. So in conclusion, in part 1, after analyzing the net force of the star, we learned that the mass of the black hole is 8.4 times 10 to the power of 43 kilograms. And in part 2, we learned that to make sure that the spaceship doesn't crash into the planet or the moon, the initial velocity must be the velocity vector of 25 times 10 to the power of 3, 25 times 10 to the power of 3, 0 meters per second. Thanks for your time.